Welcome viewers. Today we shall be discussing on the module number 37, which is on serial correlation part 1. As for the title of the module goes, we get back to the ordinary least square assumptions in the context of any regression model. In a regression model, it is observed that there is an impact of independent variables on the dependent variable in the presence of a disturbance term. So whenever we are incorporating the disturbance term, we are capturing a lot of omitted factors or unobserved factors which may or may not affect the dependent variable. However, there are certain assumptions that are needed to be done about this disturbance term. So one of the very important assumption is this, that the disturbance term across time or across space should be independent of each other. That means if the error term or the stochastic term depends on the previous period of time, whatever be the period of frequency, then we will see that there is a correlation among the different error terms of different time periods. And that is how we are inviting the word of serial correlation. So here the word serial correlation refers to autocorrelation or self-correlation, and that is basically the violation of the OLS assumptions. And if this violation is being done, then all the ideal properties of the OLS estimators will be affected. This is a problem in the context of econometrics, so the problem needs to be detected properly, and thereby the remedial measures are suggested. So in this module, we are going to elaborate on the concept of the problem of serial correlation. Then we shall highlight on the sources of this correlation, how these sources of this self-correlation appears. And finally, we shall elucidate on the consequences of this problem on the properties of the OLS estimators. So as we proceed, we find out that the definition or the concept of the serial correlation is very important. By serial correlation, we also refer to the word autocorrelation. So it means that what is meant by serial correlation or autocorrelation problem. So by the auto word, we means self-relationship among the variables. For example, the error term of the year 2022 is dependent upon the error term of the year 2021, and in this way it is dependent on the previous time periods. So if such correlation coefficient exists between the different error terms, then the covariance between the different error terms will be non-zero, and as a result of that, the problem of autocorrelation will arise. So what is actually the important concept or the definition of autocorrelation? So autocorrelation may be defined as correlation between the members of the series of observations. So whenever we are considering a series of observations which is spread across time, for example, we can have different frequency of the time series data. Either it can be weekly or it can be daily, for example, the stock prices. It can be yearly in case of the economic data. It can be quarterly in case of the financial data. So whatever be the nature of the frequency, it is quite evident that all the disturbance terms are related with each other. For example, any particular year is affected by any global shock or any local shock, then definitely that disturbance will be carried forwarded in the subsequent years. And that is how the correlation among the random terms will come up. Or this problem may also exist in the dimension of space, that is, as in cross-sectional data. Because in cross-sectional data, we are more interested with a cross-section at a particular point of time. Here the time dimension is fixed, but it varies across the cross-sections. So across the cross-sections also, it has respective random terms, and those random terms may be correlated with each other. So whatever be the nature of the data, autocorrelation is a problem of correlation among the errors of two different data points. Either it is a data point in the time domain or in the space domain. So as we come to the CLR assumptions, which is a classical linear regression model assumption, we find out that the covariance between the error terms uy and uj is equal to 0. And obviously I and j are not same, because they are the two different time periods. But in the presence of autocorrelation, we say that the errors are correlated with each other or they are dependent on each other such that the covariance happens to be non-zero. And if this is found out, then we have the problem of autocorrelation or violation of the assumption. So now we move on to how graphically we can visualize different kind of exhibitions which are shown between the error term of the current period and error term of the previous periods. If we look at the diagram of point A and point B, then we observe that in both the cases there is a particular trend. In point A, it actually follows in intervals a very systematic pattern, which means it has the points of peak and off peaks alternatively, which is very similar to a simple harmonic motion in the context of physics of the sound theory. Or if we look at the point B, then we find out that the observations are having an increasing trend. That means there is a trend observed in the series, and this trend definitely takes care of how the error terms are related with each other. If we look at the point number C and D, then we observe that they are having a declining trend in point number C, and in point number D, it reaches a peak and thereafter falls. So it is basically a kind of a peak that appears and thereby a pattern is observed. And finally, in point number E also we find out that the observations are centered around the axis. So these are all plots of the residual terms or plots of the estimated value of the error term and how the error terms are correlated with each other. So just by looking at these diagrams, we can actually infer that error terms are actually related or there is an autocorrelation effect between them. And so relation between today's error and previous time period error is captured by a coefficient which is called autocorrelation coefficient, and that is very much evident in these reflections. So here we observe either the autocorrelation coefficient is on the rise or it is on the fall or it is showing some sort of pattern. And thereby we are interested to identify in what real life situations this problem of autocorrelation appears when we are dealing with a real life data or any real data information. Now we highlight upon the sources of autocorrelation, or why does serial correlation occur. So what are the different type of cases when this problem will be evident? First of all, we refer to the problem of inertia. When we talk about the inertia, then it basically refers to the role of expectations about the future. And this inertia refers mainly to the macroeconomic variables or the macroeconomic data. So we observe that any kind of time series which is based on yearly data or annual data, for example, gross national product, or any kind of price index required for calculating inflation, or employment or unemployment, wherever they're affected by the business cycles, then they exhibit this type of inertia and the error terms are related or they follow a pattern. For example, we find out that the year 2023 may be inflationary, and the expectation is started from the year 2022. So that means any kind of error term which will be coming up in the year 2023 will be affected by the error term of 22, which is also being affected by the error term of 2021, and in that way all the error terms will carry the effect of inertia. For example, during the advent of this pandemic of COVID-19, all the macroeconomic indicators were affected from the year of 2020 onwards. So whatever has been the error term or the disturbance term of 2020 or will be carry forwarded in the disturbance term of the current year, and that is how the inertia flows on, and there is always a kind of a substantial coefficient among the error terms across the time periods. Next we move on to the second important source, which is a specification bias or excluded variable case. This is also one of the common sources of heteroscedasticity. Similarly, it is a source for autocorrelation. Because in any kind of relationship between the dependent and independent variables, it is quite absurd to capture all the variables in totality. Some variables are always left out. But if such variables are highly impacting the independent variables or the error term, then this problem will arise. For example, we are interested to measure inflation of a country and we are taking the data on money supply, but we are not taking the data on the food prices. See, if we ignore the data on the food prices, then any kind of trend in the food prices will be reflected in the error term, and the error term will be influenced by that, and it will show correlation across the different time periods. So this is actually an example how a misspecification of a model can result to the cause of autocorrelation. We move on to a very important phenomena which is observed in the world of finance and also in the world of demand-supply analysis, which is called cobweb phenomena. It's just like a spider's web. So whenever we are dealing with a supply function in the demand-supply analysis, we are always referring to a period called gestation period. For example, agricultural production cannot be increased instantly. For agricultural production to come up, this country must have to give a substantial gestation period to come up, or the period of production. So obviously we see that supply in a time period T is obviously dependent upon the current price, but more importantly it is dependent upon the previous price. Because if the harvesting is done in the year 2022, might be the bumper production can come up in the year 2023. So it requires a substantial gestation period. So the price of the output in 2023 will be influenced, or the production in 2023 will also be influenced by the previous time or the previous year's macroeconomic indicators. So this is actually referred as a cobweb phenomena. So with cobweb phenomena we mean that in any supply function, the supply of many agricultural commodities reflects the so-called cobweb phenomena, where supply reacts to the price with a lag of one time period. So always we focus on one time period as the lag because it cannot be instantaneous. Similar effect will be in case of the GDP or GNP data, where there is a lagged variable which is included in the series. And so supply decisions take time to implement. Since there is a period of one lag, the decision cannot be taken in the current period. It requires time to take up. So at the beginning of this year, planting of crops or any kind of plantation, that can be influenced by the prevailing last year. And so the supply function is always dependent on the last year's information. So what happens? The error of the current period is automatically influenced by the error of the last year period. So this will evidently give rise to the problem of autocorrelation. So autocorrelation will be very much evident in this cobweb model. Next source, which we have already pronounced in the previous slide, is about the term lags. So when we talk about the term lag, we basically refer to the information of the past period. That period can be of any frequency. It can be the previous day or previous week or previous month or previous year or previous quarter. So whatever be, the lag variable plays an important role in causing the problem of autocorrelation. For example, we say that consumption expenditure and relationship with income. This is a very common example of any regression model. But consumption not only depends upon the level of income of the current period, but also consumption of the previous time period. For example, in the previous time period, the individual was very wealthy. So he was following a very high level of standard of living and a high lifestyle. But say after the pandemic, his major sources of income has come down. So he needs to actually go for a more structured and a more disciplined standard of living, or rather he has to cut down the expenses. But actually what happens, suddenly cutting down the expenses will be difficult for him because his consumption standards are greatly influenced by the comforts that he enjoyed in the previous time period. So this type of example shows that consumption is not only a function of income of the current period, but also it can be the function of its own variable in the last period. So what we observe? We observe that consumption T minus 1 is one of the lagged dependent variable. So any kind of modeling where the dependent variable is the becoming lagged or independent variable becomes the lag dependent variable, then the problem of autocorrelation is confirmed, because we can see how the error terms will be related to each other. So this is one of the very important theory of investment, where investment is also dependent upon the investment in the previous year. So automatically they are correlated with each other. So past year's information is affecting them, and that is how the importance of lags give rise to the problem of autocorrelation. Next, we have a kind of an exercise which is being done whenever people are engaged in the data analysis. So in case of the data analysis, we see that sometimes this word is spelled out as data gets manipulated. So any kind of manipulation is being done by actually converting a monthly data into yearly data, or by taking the averaging, or any kind of data transformation might also lead to the problem of autocorrelation. So might be it is controlling the level of fluctuations, but on the other hand, we will observe that the error terms might be becoming correlated with each other when any kind of such kind of mechanism is adopted. So it is said, so graph plotting quarterly data looks more smoother than the monthly data. So if we are not interested with the quarterly data because it is showing a pattern and we want a smooth trend, we may convert quarterly to monthly data. But by doing so, we are basically smoothing the level of fluctuations. But on the other hand, we are introducing autocorrelation. So there is a general tendency of converting a quarterly data to a monthly data, or a monthly data to a yearly data, but actually we are looking up the smoothing the level of fluctuations. But on the other hand, we are inviting the problem of autocorrelation. So this is one of the most important source which we find when we work with the data as a researcher. Next, we go for a very important case which is considered by the time series econometricians, that is the data transformation. Suppose I collect the data of the GDP for a particular time frame, say from 2000 to 2020, and I find out that GDP series is showing a trend. So in order to get rid of the trend, I actually take the subtraction from the last period or the last year, and thereby I do the difference. So if I do the differencing and I find out the error term is not showing any pattern, then I can say that autocorrelation is eliminated. But actually in most of the times what happens, not only the number of observations are lost, but also sometimes the autocorrelation problem remains as it is. So even after data transformation, we observe that the autocorrelation comes in, where we find out in the first equation, yt is a function of xt, all are in the current periods. That means current value of y is dependent upon the current value of x. But in equation 2, we observe the value of y in the last period t minus 1 is dependent upon the value of x in the last period t minus 1. So both are the lagged information. So if I take the difference between 1 and 2, that is subtracting 1 minus 2, I get delta yt, which is yt minus 1, and then I get beta 2 as it is as a common. Beta 1s are getting cancelled out, and I get delta xt and finally delta ut. So this transformation explains how the sources of autocorrelation can come up. And finally, we can say that this type of transformation may invite the problem of serial correlation. So hereby, we can also identify some of the major terminologies which will detect the problem of autocorrelation. So what are those? Non-stationarity. So this slide we are actually defining when we consider a data to be stationary or non-stationary. Stationary means that the mean and the variance do not change with time. So as I increase the number of observations, my mean is changing or the variance is rising. These are not to be done in a stationary data. But if the data is showing any trend, or the data is showing a changes in the mean and variance, then definitely it is showing the pattern of autocorrelation. So this is one of the sources of autocorrelation. So here we observe the particular sources of autocorrelation which mainly arises from the presence of lags, the presence of cowboy phenomena or manipulation of data, or we invite the term non-stationarity in the data set, or it can be due to the misspecification or any kind of inertia that the variable is already having. And thereby the sources of autocorrelation are evident in any kind of real life time series data. Now we focus on the types of autocorrelation. So by types of autocorrelation we mean either a positive trend or a negative trend is to be observed. If it's a positive trend, then it's a positive autocorrelation, otherwise it's a negative autocorrelation. Moreover, we can have two more defined types, which is pure and impure. So by pure autocorrelation we mean that the autocorrelation is of first order, which means the error term in the time period t is dependent upon the error term in the previous time period with a coefficient which is called ρ1, and this ρ1 is called autocorrelation coefficient because it captures the correlation between the error term of the current period with that of the previous period. And so the value can be positive or negative, and we can say when it is positive or it can be negative, or this does not exist, then no autocorrelation problem. Sometimes we deal with a seasonal data, then we can go for 4 quarters and thereby we can go for row 4. Secondly, we can move on the impure autocorrelation. In impure autocorrelation, we cannot identify the source of autocorrelation, nor can we calculate the autocorrelation coefficient ρ. So here the problem is either it is inherent in the functional form, or due to any kind of omitted variables, or we drop a variable and we check, or we go for a better specification like data transformation as we do in heteroscedasticity, and we get rid of the problem. So impure autocorrelation is very difficult to deal with because the actual cause of the problem cannot be identified. So this autocorrelation types basically refers to the 4 types: positive, negative, pure and impure. But whatever be the problem of autocorrelation, there will be some kind of consequences on the properties of OLS estimators. Now we focus on the most important segment of this module, which is on the consequences of autocorrelation. That means if the autocorrelation problem is taken up and if it is not rectified, then what would be the impact on the properties of ordinary least square estimators? As a whole, we can identify the major impacts, that is, estimated coefficients will be remaining unbiased and consistent. Just like the ideal properties of OLS, it will again retain the unbiasedness property as it was done in heteroscedasticity and also consistent. Standard errors will be biased, and so inference will be very difficult to come up. And this will make the dependent variable to be less affected by the independent variables. That means it will be affecting the statistical significance of the independent variables, and also the t-scores will be incorrectly too high. So maybe the t-score high is very much desirable, but here this high is because of some kind of properties that these OLS estimators will be failing. So now we focus on the first impact on the unbiasedness property. So in this particular slide, we take up a model which is yi equals to alpha plus beta xi plus uy. So we observe that alpha is the intercept term, beta is the slope coefficient, and xi is the independent variable. Now we convert the capital letters to small letters and we find out these are the deviations from the means. And on the basis of that, we actually state the expression of beta hat OLS, which is summation of small xi small yi by small xi square. So in place of yi, we substitute the expression of the model and then we divide by the common denominator in components. The first one is summation xi in the numerator, but it will be 0 because it's a deviation from the mean. The second one is beta only because the numerator and denominator are getting cancelled out. And the last one is about the correlation between the xi and uy as far as the assumption is concerned. So as we all know that xi is a non-stochastic because there is no relation with the error term. So after taking the expectations, we observe that expectation of beta hat equals to beta, and thereby beta hat is an unbiased estimator of beta, just like a normal OLS estimator. Now when we focus on checking the variance of this beta hat OLS under the presence of this problem, then we observe that variance of beta hat is basically taking ki uy whole square, where ki was the weight assigned under the OLS estimation, which is small xi by summation of xi square. So where we have the own terms like ki square, uy square, and also the cross terms, which is very important here because the cross term shows the correlation among the errors of different time periods where I and j are not equal. So with the first term, we are already with the variance of beta hat OLS, usual variance under OLS assumptions. But with the second component, we observe 2 summation ki kj because it is actually the cross terms, expectation of uy uj. This expectation of uy uj will no longer be 0 in the presence of autocorrelation, so it will be non-zero. And since it will be non-zero, we are basically looking into some kind of a variance under this case, which is higher than the ordinary least square variance under OLS, which means sigma square u by summation xi square. So we can see that beta hat OLS is not having the minimum variance property or the blue property as it was supposed to have under non-autocorrelation. So the minimum variance property will be violated in the presence of autocorrelation. So what we actually sum up in the consequences of autocorrelation, that OLS estimator is unbiased, which is retaining, but the OLS estimator has no minimum variance property. So it does not satisfy all the blue properties. Maybe it is satisfying the unbiasedness property, but not the minimum variance property. So now we go for the summing up of this particular module, where the module highlights on the concept of autocorrelation, that is basically the definition, the areas when this autocorrelation will arise, mainly the sources, and finally it will be considering on the consequences of autocorrelation. That is very important because the OLS estimators will be getting affected either in terms of the violation of the minimum variance property despite the unbiasedness property is retained.